Welcome to The Explainer. Today, we're taking the 10 most absolutely critical concepts in cloud computing, and, well, we're bringing them to life. We'll be tracking the actual life cycle of a modern application. So if you've ever wondered how the internet actually handles massive, global scale under the hood, you are in exactly the right place. Let's jump right in.
Okay, picture this. You've just launched your brand new app. At first, traffic is, pretty flat. Crickets. But then, bam, it gets featured on a massive news site and your traffic graph just explodes literally overnight. Now, for a traditional old-school setup, this kind of rapid influx of users usually means one thing: a crashed web page and a totally dead application. So the big question is, how do we actually survive this?
Well, here's our roadmap for doing exactly that. We're going to take an application from barely surviving a traffic spike all the way to effortlessly running a global empire. We'll hit handling viral traffic, modernizing compute power, connecting services, data storage, and safety, and finally wrap up with automating the infrastructure.
Right, so our very first hurdle is simply keeping the lights on. Let's look at Chapter 1, handling viral traffic, specifically scaling and load balancing. Now, the old way to handle a spike was vertical scaling. You basically just had one machine, and when traffic surged, you tried to beef it up. You'd buy a bigger CPU or shove in more memory. But you hit diminishing returns incredibly fast. I mean, a 116 GB memory stick might be $100, but a 64 GB stick, that could be $600. It gets crazy expensive. Plus, and this is the real kicker, if that one single beefed up machine goes down, your whole app dies. It's a massive single point of failure. Horizontal scaling uses a totally different paradigm. Instead of building one giant, expensive machine, you just clone your application across multiple, way smaller, cheaper machines. If you have 5 cheap machines and 2 crash, the other 3 just keep humming along serving your users. You get much lower costs and significantly higher stability. But horizontal scaling introduces a fun new problem. If you have 5 machines running, how do you know which one to send your brand new user to? Enter the load balancer. This sits right in front of your horizontal fleet, acting basically like a traffic cop. It uses some pretty clever algorithms to distribute traffic only to the healthy instances. It might use round robin, just iterating through machines one by one, or for a more intelligent approach, it might look for the instance with the least connections. Or even smarter, the lowest resource utilization, meaning it routes a user to a machine sitting at, say, 20% CPU, rather than the one struggling at 99%.
And of course, nobody wants to be sitting at their desk at 3 a.m., staring at server graphs, manually clicking buttons to add new cloned machines during a spike. That is exactly where auto-scaling comes in. You can hook your system up to track specific metrics, like overall CPU utilization. When traffic surges, auto-scaling automatically provisions and adds new instances to your load balancer. And the best part? When the viral spike eventually fades and traffic drops, it automatically removes them, saving you a ton of money. Okay, so we survived the traffic spike, but managing all these individual virtual machines is still a huge headache. Let's move to Section 2, modernizing compute power with serverless and containers. This brings us to a massively popular but kind of heavily debated topic right now: serverless. Originally, with services like AWS Lambda, true serverless meant you just wrote your code and the cloud provider handled absolutely everything else. You didn't know or care about the underlying servers, and crucially, you only paid for the exact milliseconds your code executed. No idle costs whatsoever. But definitely be careful out there today. The industry definition is getting super blurry. Providers are now slapping the serverless label on things where they manage the scaling, sure, but you're still forced to pay a pretty hefty monthly bill for the underlying instances running behind the scenes. True serverless is pay-per-use, but the marketing term has definitely evolved. Another absolute game changer for modernization is container orchestration. You probably know containers. They bundle your code and all its dependencies into one isolated package, which completely eliminates that classic developer excuse, well, it works on my machine. But deploying and monitoring hundreds of containers manually, impossible. That's why we use orchestrators like ECS or Kubernetes. You literally just tell the service, hey, I want 3 copies of this container running. The orchestrator handles deploying them, hooking up the load balancers, and if a container runs out of memory and crashes, it instantly detects it and spins up a fresh one. All right, our compute power is modernized, and our app is starting to grow into a bunch of different internal pieces. Let's dive into Section 3, connecting and decoupling services. Let's look at how we used to do this, the traditional synchronous request-response model. Imagine an order-taking app. An order comes in, and the main app synchronously calls the credit card service to charge the customer.
If that works, it calls the warehouse service. Then the fraud detection service. It's basically a house of cards. The glaring issue here is tight coupling. The main order app has to know exactly how to talk to every single downstream service. If the fraud service happens to crash, the entire order process might just hang or completely break. The modern cloud answer to this is event-driven architecture. Instead of synchronously calling downstream services, the main order app simply publishes a notification. Think of it like an envelope of data containing the order details. It drops this envelope into an engine like SNS or EventBridge. That engine then fans out copies to any service that's subscribed to it. The credit card, warehouse, and fraud services all receive the event simultaneously and process it independently. The really beautiful thing? The order app doesn't even know these other services exist. It's completely decoupled, which means you can easily add new features later without ever touching the original code.
Now, obviously, all these services need to communicate safely. Back in the day, companies used physical server rooms and physically hardwired subnets to separate public-facing apps from private databases. In the cloud, we use cloud networks. These are completely isolated virtual spaces inside the provider's massive data centers. So even though you're physically sharing infrastructure with other companies, your cloud network ensures absolute isolation. You set strict inbound and outbound rules, meaning your internal databases can be literally invisible and unreachable from the public internet.
Okay, our services are humming along in perfect decoupled harmony. Let's move to Section 4, Data Storage and Safety. The somewhat overwhelming world of cloud storage really just breaks down neatly into three main pillars. First, object storage. This is basically your general-purpose dumping ground for media files, JSON configs, or CSVs. Next, you have block storage. Think of these as virtual hard drives or volumes that you attach directly to your compute instances, perfect for heavy processing jobs. And finally, databases. This covers everything from your traditional relational SQL databases to flexible NoSQL document stores and even lightning-fast in-memory cache solutions. But no matter where you keep that data, you are going to see uptime guarantees that look exactly like this, 99.99999%. So what does a number with that many nines actually mean in the real world?
Well, that metric relates to availability. It essentially measures how often your application is actually up and running. A percentage that high means you're only expecting a few minutes of downtime across an entire year. Cloud providers pull off this magic trick by hiding some incredible physical infrastructure behind the scenes. Specifically, they use availability zones. These are physically separate data centers or entirely distinct partitions within a building, with totally separate power grids and internet lines. By horizontally scaling your app across these separate physical zones, even if one entire building loses power, your app doesn't blink.
But you've got to make sure you don't confuse availability with durability. Durability is specifically about your data's ultimate survival. When you upload a file, the cloud provider doesn't just stick it on one hard drive. They automatically create multiple copies and scatter them, sometimes across entirely different geographic regions. Honestly, a hard drive could literally catch on fire and explode, and you wouldn't lose your file. The cloud just instantly recognizes the loss and self-heals by replicating a new copy from the surviving backups.
Which brings us to our grand finale. Section 5, automating the infrastructure. Here's the deal. How you build all this matters just as much as what you build. The old way of building cloud architecture was logging into a web console and manually clicking buttons to create databases and servers. Honestly, that is incredibly dangerous. It is so prone to fat finger mistakes, like someone accidentally clicking delete and wiping out production. Plus, if you need to replicate your North American setup in Europe, you have to manually click through the whole miserable process again. The modern solution is infrastructure as code, or IAC. Using tools like Terraform or the Cloud Development Kit, you write actual code that defines your entire infrastructure. You put this code in Git, your peers review it, and then the cloud provider reads it and builds everything perfectly on your behalf. Want to deploy a clone to Europe? You just change one variable in your code and hit deploy. It is safer, trackable, and infinitely repeatable. And just like that, we've completed our life cycle journey. We went from a single, struggling machine to a horizontally scaled, serverless, decoupled, highly durable, and completely automated cloud architecture. So as you look at your own projects, I have to ask, are you just clicking around in the console trying to survive today's traffic? Or are you actually utilizing these incredible cloud paradigms to effortlessly scale for tomorrow? Think about it. Thank you so much for joining me on this explainer, and I'll catch you in the next one.